Thank you. So this is joint work with David Hernandez. And if you don't want to take notes, you can upload our paper from the archive. It was uploaded a few weeks ago. And I want to say, like Misha this morning, that when I was preparing this text in January or February, I was really looking forward discussing this with Andrei, because I always cared a lot about his opinion on mathematics and in particular also on what I was doing. So unfortunately this will not be possible. One reason why I valued a lot his opinion is that he was very honest, and he would not pretend that he likes something if he doesn't like it. So if he said that he liked it, it was really true. And I remember back in '94, I think, he was asking me what I was interested in, what I was up to, and I told him I want to calculate decomposition numbers of Hecke algebras at roots of unity. And he told me, but why are you interested in such things? And for him, this business of modular representations was not something attractive. And anyway, so okay, today I'm going to discuss about quantum affine algebras. So let me give you first an introduction. So as in the first talk this morning, we start from G, a simple Lie algebra. Over the complex number. And then we consider the corresponding affine Lie algebra, G hat. And finally, we take the quantum version of this, that is a quantum enveloping algebra of this UQ G hat. And here I want to consider this as an algebra over the complex numbers, meaning that I take Q as a complex number, non-zero complex number, and not a root of unity. That's right. Okay, and so we want to study the category of finite dimensional representations of this quantum affine algebra. And so this is a Hopf algebra, so it means that this category is a tensor category. And it has been studied by many people. It's impossible to make an exhaustive list. The irreducible representations have been classified by Shary and Presley beginning of the 90s. And then there were some important work by Frenkel and Reshetikhin, who introduced the notion of Q character for these representations. And then there were works by Kashiwara, by Ginzburg-Wassereau, and then end of the 90s, there was also the geometric approach by Nakajima, who explained how one can understand this category in the simply laced case using graded Nakajima varieties, graded Nakajima quiver varieties. Okay, so then in 2010, David and I started our joint project, and this is a continuation. And basically, what we wanted to do was to relate this representation theory, which has a lot of nice combinatorial flavor, to relate it with the theory of cluster algebras. So relate with cluster algebras. So let me state in a little bit vague way what was the main result of our first paper. So we introduced a certain sub-tensor category in this. This is a huge category. I mean, if you just look at the parameterization of simple objects are parameterized by discrete parameters, but also by some continuous parameters. So it's really very, very big. So we introduced some kind of small subcategory in there. So there is a tensor subcategory, which we denoted by C1 for some reason. I don't want to go into that, of this rep UQG hat, such that two things: the Grothendieck ring of this tensor category C1 is a cluster algebra. Of finite type, and we know that the cluster algebra of finite type are classified by the same Cartan-Killing classification. So here it is the same type as G. Yes, so here I'm assuming G is simply less at this stage. I should have said this. So here, suppose G of type ADE for this theorem. So first point, that you can identify the Grothendieck ring of the category with a cluster algebra of the same finite type as G. And the second more important thing is that in this identification, the natural basis here, which is the basis of classes of simple objects, so classes of simple objects, this coincides with a set of cluster monomials. Okay, so in fact, to be correct, in our paper with David, we were able to prove this in type AN and D4, and we conjectured it in the remaining cases, and then it was proved by Nakajima in full generality. So I think it's an important, it's a nice result, because it allows to calculate. I mean, this Grothendieck ring now has a totally combinatorial description, because for cluster algebras of finite type, we have a full description of what are the clusters, what are the cluster variables. We have this nice associahedra which describe, I mean, all the combinatorics. Okay. Now there are two weak points. However, in these two weak points, which I want to underline in this result, first of all, as was pointed by Maxim, this is only for simply laced. And also the second point is that this subcategory C1 is really very small, so it doesn't capture a big piece of the category. So what I mean, for example, I will be speaking in a minute about Kirillov-Reshetikhin modules, which are some special family of irreducible representation in this category. So this is an infinite family, but only very few Kirillov-Reshetikhin modules belong to this category C1. So only 3 for each node of the Dynkin diagram. So it's a very small category. Still, it has infinitely many simple objects. because there are infinitely many cluster monomials. But okay, so C1. Well, you know the parametrization of simple objects by Drinfeld polynomials, right? So we put a restriction on the possible roots of the Drinfeld polynomials. So the Drinfeld polynomials can be, so you have your Drinking diagram of G, which can be put into, which can be colored with two colored. It's bipartite, right? And then for every black node, you allow only the roots 1 and q square, and for every white node, you allowed only the root q and q to the cube. And then you want that every composition factor of an object in your category has only these two possible roots in the Drinfeld polynomials. So it's a very strong limitation, of course. So this C1 is very small. So today I want to try to remove these two conditions in some way. Of course, the result will not be as complete as it is here, but still it can be seen as a first step. So first, G does not have to be simply laced. And then the second condition is that the second improvement is that we replace this category C1 again by a certain tensor subcategories, but this one is going to be much larger. So we denote it by, so replace C1 by a much larger. No. No. By much larger tensor category, subcategory. And here by much larger, I mean that every reducible representation in here can be written as a tensor product of irreducible representations, and each of these factors will belong to this C1 up to spectral shift. So if you are able to describe all the simples in here, you have already a very good understanding. Right, okay. So this is the plan. And now let me give you an overview of the result. So by this I mean that I postpone some precise definition to the later section. I just want to give you an idea of what kind of result we can prove. So we start from this Lie algebra G, of course, and what we do is that we attach to this Lie algebra, or to the Cartan matrix of this Lie algebra, a certain quiver. And I will give you the precise recipe in a moment. And then from this quiver, I think it will be denoted G minus. So G doesn't mean group. There is no group here. So G like graph. And minus because it's going to be attached to this category C minus. I should have said by a much larger category, which I denote by C minus. Sorry. You will see why in a moment. So with this quiver, we can attach two different algebras. We can consider this quiver as the initial seed of a cluster algebra. So this will give rise to a certain cluster algebra. I think everybody is comfortable with the definition of a cluster algebra. Here I'm talking about cluster algebra of geometric type. So there will be no coefficients, no frozen variables. And so it's enough to give and also it's a skew symmetric. So even, maybe this is something to stress, that even when G is non-simply laced, the quiver here will, the cluster algebra here will be skew symmetric and not skew symmetrizable. Okay, and also to the same quiver, if we add a certain potential on this quiver, like in the talk of Daniel yesterday, then quiver with potential gives rise to some Jacobi algebra. So let me denote by script A, or by this A, the Jacobi algebra. Okay. And now, what can we say? So the first theorem, let's say theorem 1, will be that this tensor subcategory C minus will have Grothendieck ring isomorphic to the cluster algebra A corresponding to this quiver here. Okay. So this is somehow a replacement for the first statement here. But this is not the difficult part. In fact, the difficult part is really this one. And for this, we don't have a complete answer. We are not able to show that all the, that all the cluster monomials, let's say, in this cluster algebra correspond to classes of simple objects. But we can prove it for a subset of the simple objects, which are the Kirillov-Reshetikhin module. So let me recall that there is a distinguished family of irreducible representations. Finite dimensional irreducible representation of this UQ of G hat, which are called the Kirillov-Reshetikhin modules. And the usual notation is the following: W, and then you have three parameters, I, K, and A. So I is a node of the Dynkin diagram. Okay, this means the vertices of Dynkin diagram. K is some non-negative integer. And A is a complex non-zero parameter, which is usually called spectral parameter. So these are defined using the classification of irreducible modules given by Shari and Presley. So in order to specify an irreducible representation, you just have to specify its set of Drinfeld polynomial, and this is encoded in these three things here. So if you are not familiar with this, let me just give you the intuition behind this. Of course, UQG hat contains UQG as a subalgebra. So if you restrict finite dimensional representations of UQG hat, you get finite dimensional representation of UQG. They do not remain necessarily irreducible, but still you have somehow a highest component if it is not irreducible, and this highest component in the case of this Kirillov-Reshetikhin module would be you take the fundamental weight pi I, and you take k times this pi I, and so this should be seen as a kind of family of quantum affine analogues of this irreducible representation with highest weight k pi I. Okay, so now I can tell you, I can give you a better idea what is this category C minus. So this Kirillov-Reshetikhin module will belong to the category C minus if the spectral parameter A is of the form Q to the R, where R belongs to the negative. So this is why I have this minus in the notation. And it's almost an equivalence. I mean, there is some parity condition here. According to the node of the Dynkin diagram, you need to put even or odd. I don't want to specify this. I think it's not so important. So in particular, you see there is no limitation on K. That's the most important thing, because when you have the character of a Kirillov-Reshetikhin module for a given I and K and a given A, then you can just shift in a trivial way by multiplying by the new spectral parameters. So now I can state, so because of this, I will simplify the notation. So from now on, I write WIKR instead of WIKQ to the R. So I drop this Q in the notation. So there will be two integers here and the node of the Dynkin diagram. Fine. So now let me remind you also that Frenkel and Reshetikhin, I said it already, but I think it's important to write here. Frenkel and Reshetikhin introduced what they called Q character. So given an object in this category rep UQG hat, they attached what they denote by chi Q of M. And this is a certain Laurent polynomial. There are several equivalent ways to describe it, but one way is to say that you can decompose these representations as a direct sum of so-called loop weight spaces. And then this is a Laurent polynomials whose coefficients are the dimensions of these loop weight spaces. And the monomial encodes the loop weights corresponding to these weight spaces. So they call it Q character. In the sense that if two irreducible representations have the same Q character, then they are isomorphic. But this doesn't work if M is not irreducible. So this, in fact, if you consider the ring of Q character, then they show that the ring of Q character is isomorphic to the Grothendieck ring. So, in fact, passing from the representation to its Q character is like taking the class in the Grothendieck ring, right? So it's a kind of semi-simplification. So this means that here in this first theorem here, I could think of this Grothendieck ring as being the ring of Q character. And let me think of it in this way. So you mean this Q that they have in the notation? Yeah, I think this is a Q. Yes. You know, when you write, it's not a polynomial in Q. No, sorry. It's a polynomial in some formal. It's a Laurent polynomial in some formal variables. In general, some formal variables which are written like this, where I again is the same node of the Dynkin diagram, and A is some arbitrary complex number. And in this subcategory C minus, the only A which also will be involved will be again integer powers of this Q, right? But so you should think of this again as a fine analog. This is a fine analog of the formal exponential of the fundamental weight by I. When you write ordinary characters for UQG module, they are written as polynomials or Laurent polynomial in these guys. And these now are some version which contains additional spectral parameters.
But it actually does not depend on Q, this character. This is only a name of the variable.
Yes, I'm not responsible for the name actually, so you should. Yes, when you expand, when you look at these Q characters, we'll see examples later. The coefficients are just integers; they don't contain Q at all. It's only in the name of the variables, the variables which are involved. Okay, so the second theorem is that if you take a Kirillov-Reshetikhin module in this subcategory C minus, then again, if we identify this with a ring of Q characters, what I'm saying is that the Q characters of these guys will be some special cluster variables for this cluster algebra. Then chi Q of this IQR is a cluster algebra, is a cluster variable for A. Okay? Does it make sense? Yes? For F, sorry, K not Q, so excuse me, yes. So, yes. A. I'm going, yes, this will be my third paragraph. I'm going to give you the precise definition of this algebra in a second. Just be patient. I'm almost finished with this overview. But, I mean, I need some combinatorics to do that, and I don't want you to be bored before I come to the statement. Yes? No. Of course, you have to make lots of mutations, and I will describe also this sequence of mutation that you need from the initial seed. I mean, the initial seed will consist of Kirillov-Reshetikhin modules, but you don't have all of them. I mean, I will say more a little bit later. So I want just to now give two main applications of this second theorem. First application is that this gives a new algorithm for calculating these Q characters using cluster mutations. So I'm not saying that this algorithm is really practical, but it is still it's totally different from the algorithm of Frenkel and Mukhin. They also have an algorithm for calculating Q characters of certain representations, which works in particular, as was shown by Hernandez and Nakajima, for the Kirillov-Reshetikhin modules, but it proceeds in a totally different way. And the interesting thing is that now not only we have an algorithm, but we have all the framework of cluster algebra that we can use, and in particular, we can use the deep theory of Derksen, Weyman, Zelevinsky, because they have shown that for cluster algebra of the type that we have here, geometric types, Q-symmetric matrix, that you can give some geometric formulas for the cluster variables by using the Jacobi algebra here, and each cluster variable corresponds to some distinguished module over the Jacobi algebra, and then you can express this cluster variable. Its coefficients will be Euler characteristics of Grassmannian of sub-objects for the corresponding representation. So this yields some geometric formula for the Q characters. So for KQW IKR. And these formulas are compatible with tensor products. So you can even, when you take tensor products here, it means that you take direct sums for the corresponding module for the Jacobi algebra, and then you take again the same Euler characteristics associated with these direct sums. So in particular, we can apply this when k is equal to 1. So these are the fundamental modules when k is equal to 1, and take tensor products of this k equal 1, and we obtain in this way the standard modules. And so we get some geometric formulas for the Q character of the standard modules. And if you compare this with the geometric formulas given by Nakajima in type ADE, if you compare the varieties, so it follows from some result of Lustig that in type ADE, the Grassmannians of submodules that come from this Jacobi algebra are isomorphic to the fibers of Nakajima. So in type ADE, we recover the geometric formulas of Nakajima. So what this suggests is that when we are in the non-simply laced case, then the Grassmannian of submodules for this Jacobi algebra, which I will show you, might be some kind of replacement, because we don't have Nakajima theory available for non-simply laced case. Okay, so now in the remaining half an hour, I want to describe precisely for you this algebra and this Jacobi algebra, and how we mutate things to calculate these Q characters. Okay, so as I said, we have to start. So the cluster algebra A. So we have to start producing a certain quiver. So this will be done in a few steps, but the first data is the Cartan matrix of G. So we know that this is symmetrizable, so it can be written with the usual notation. We can write B equals DC, where D is a diagonal matrix, and B is symmetric, in the usual way. So this B, I will denote its entries by Bij. Okay. Now, from this, we now can define a certain graph or quiver. So the first graph I define, I will denote by gamma tilde. The vertices, set of vertices, you take I times Z. So it has infinitely many vertices. And what are the arrows? That's very simple. And it's totally uniform. Namely, if we have a pair IR and a pair JS, there will be an arrow from IR to JS if and only if S is equal to R plus the entry Bij of this symmetrized Cartan matrix here. Yes. So it turns out that when you draw this infinite graph, it is not connected, and it has two connected components which are isomorphic. So this is a very easy lemma. Now this gamma tilde has two isomorphic. This is related with the fact I was saying before that in this category C minus or C1, we have some kind of even or odd conditions on the spectral parameters as two isomorphic connected components. And so you pick one of the two, which one you want. Pick one and call it gamma. And the vertex set of this I will denote by V. So let me see. I have prepared some examples here. Oops. So you can still see the definition here. So here I prepared the examples of A2 and B2. So the vertices are pairs, as I said, I, comma R, where R are some integers, and since it is type A2, we only have one or two on the first component. And for example, well, the Cartan matrix in type A2 is already symmetric, and it's like this, right? So we have arrows going from 1 minus 4 to 1 minus 2, because B11 is equal to 2. So we add 2, and then again, and then again. It's infinite, of course, in both directions. And then for these two entries, minus 1 here, we get some arrows going down, 1 minus 2 to 2 minus 3. So here there is a shift of minus 1. Yes? Yes, so that's a very good remark. So in this A2 case, and more generally in the ADE case, what we get is exactly the Auslender-Heighton quiver, including the arrows for the translation. So normally what people call Auslender-Heighton quiver, you would not have these vertical arrows. I mean, you have them if you wish, but they have a special status. They correspond to the translation. So in type ADE, this is precisely this graph. But now in type non-simply laced, like this B2, this is going to be a little bit different, because you see, now, in type B2, the Cartan matrix is going to be, I mean, after multiplying by this matrix D, the matrix B in type B2 is going to be this one. So you will have, so I draw it in this way in order to have a planar graph. So I put the vertex 1 in two different columns like this. And so, because of this entry 4 here, the vertical arrows on these two columns, they have a shift of plus 4 on every second entry, whilst in the middle column you have a shift of plus 2 only, and then you have this going down arrow, which always shift by minus 2. So you get this graph here. Is that okay? So this is almost it, but we still have to make some modification. Sorry? When you... No, I think the only property that we use to prove that is that well, in a sense, yes, is that the Dynkin diagram is a tree. I mean, if a Dynkin diagram is a tree, even if it is not of finite type, then you will still have this same property. Sorry? Yes, somehow, yes. I guess so, yes. I guess so. I really only thought of the Dynkin case, but probably yes, yes. Okay, so this is, I mean, this one should think of perhaps of the graph associated to a bigger subcategory, which I would call C index z, for example, for z for integer parameters. But now, as we saw, we cut the parameters and take only negative powers of q. And this means that we have to cut also our graph and take only kind of half infinite one. So let me explain how you do that. So for this, I have to introduce, I'm sorry for that, some notation. We need a certain change of labeling. A change of labeling of the vertices here. So it's a very trivial one, but still we cannot avoid it. So here V is a set of vertices of these graphs, which are called gamma. And I just want to translate the second component by di. OK. And this letter V and W are supposed to remind you of the notation of Nakajima for Nakajima varieties, where he's also using W for and V for with reference to highest weight or weight inside the representation. So it's a little bit like this here. Anyway, so now let me call the same graph, but with new labeling by W. I will call it G. Okay. So I have this graph gamma. Now, if I just change the labeling by using this stupid bijection here, then the new graph, I will call it G. I have to use this two labeling. It's unavoidable somehow. And then what is going to be G minus? So G minus is di are the entries of the diagonal matrix D, which is used for symmetrizing the Cartan matrix. Yes, so in this case, D1 and D2 is 1, so it's just a uniform shift of the second coordinate. But in this case, D1 is 4 and D2 is 2. Sorry, here the two D's are equal to 2, and here 4 and 2. So it produces a little bit different graph. So G1 is G minus is a full subgraph of G with vertices W minus, and W minus, as you may think, is the subset of vertices where R is negative or 0. So let me do it more concretely here. It means that I start changing the, maybe I use a second chalk. So here it's going to be 0. Here it's going to be 1. It's going to be 2, etc. Sorry, no. What am I doing? So I'm adding 2. Yes. So here I had minus 2. It's going to be 0. Here I had, yes, OK. And here it is minus 1. Here I had minus, so it's going to be minus 2, etc. And here plus 1, 2, etc. So this is a graph now with a new labeling, G. Here we are in type A2, so di is equal to 2. No, sorry. No, I'm mixing up, sorry. D1 is 1. Excuse me. I'm mixing, but they are proportionals, that's why. I'm mixing entries in these and OK, so di is 1. So I have to start again. OK, I'm going too fast. You cannot. OK, so something like this will happen. 1, 0. After changing the labeling, I will get something like this. And then I erase all the vertices which are at altitude higher than 0. OK, so left with something like this. Okay, a half infinite part of this graph. And then if I do the same in type B, somehow I will get, for example, some graph like that one, where I'm just forget about the labeling, perhaps. If I copy it from my paper, I will avoid mistakes. Like you would obtain 0, -1, -2, -3, -4, -5, etc. Okay, it's not so important. So you have a half infinite graph, and now the definition of the cluster algebra is clear. So definition of A. So we take this graph. It's an infinite graph, but nevertheless, we can attach to every vertex a certain indeterminate. So we have we define some commutative variables z. So z I r, where I r belongs to this w minus. Okay, and then we say that A is the cluster algebra with initial seed given by this z and the graph G minus. So by this I mean that you consider the ring of rational function in these variables with rational coefficients, and then we have this procedure of cluster mutation. So starting from the variables themselves, we can mutate, and we collect all the cluster variables obtained from this initial seed after a finite sequence of cluster mutation. And yes, we do. Yes, we do. And it's true that there is not much literature on cluster algebras of infinite rank, and here, in fact, it's just to make the statement a little more easy to write, or more pleasant to state, let's say, because in the things which I'm going to explain, we could, instead of this infinite graph, we could take just a finite portion of it, but arbitrary large finite portion of it. So I think it's more nice to state it directly in the infinite case. But all the cluster variables which I'm going to mention will be obtained using only a finite sequence of mutation. Although it's, well, you will see. Okay, so
Can you allow also positive powers of Q? And you have a theorem about two-sided graph or something?
No, I don't have a theorem about two-sided graph at the moment, and I think it would be, I mean, I have some ideas what happened with two-sided graph, but it's more complicated, so maybe we can discuss it later if you wish. Okay, so now I want to state more precisely this theorem here. So I want to explain what is a sequence of so in order to generate cluster variables, you need to do sequences of mutations. And the claim is that there is some very nice and particular sequence of mutations which will give rise only to kind of Kirillov-Reshetikhin modules. So we will state in the word of Kirillov-Reshetikhin modules by using this particular one. So there is a, and
You're not telling us the representation theoretic meaning of this initial variable. They're just formal variables.
for the moment they are just formal variable, yes. So there is a distinguished sequence of mutations. Let me call it S, and then I plan to show you on some slides how it goes, because I don't want to bother you with too many combinatorial definitions. So there is a certain distinguished sequence of mutation S such that well, as we know, when we mutate the graph, the quiver changes. But sometimes we can get back to the same quiver. And this is the case if I take mu of this S, so meaning the sequence of mutation corresponding to this and then the let M be at least what is it? The half of the dual Coxeter number. If M is like this, then if you take mu S to the M and you applied it to the initial seed, then this new seed will contain characters, Q characters of all Kirillov-Reshetikhin modules up to spectral shift. So perhaps I show you on this. So I have to pull the. Sorry. What is the same? You mean the sequence S? Well, you will see. I just want to show it. Yes, they do. In fact, I'm cheating a little bit everywhere here. I should say truncated Q characters all the time. So the point is that when we start in the beginning, we have already Q characters of the Kirillov-Reshetikhin module, but they are truncated in such a way that you remove all the monomials except the monomial corresponding to the highest weight. And then by applying this sequence of mutations, you kind of replace the Kirillov-Reshetikhin modules by new Kirillov-Reshetikhin modules with spectral parameters shifted below. And then when you repeated this enough time, then you end up having truncated Q characters which are not truncated anymore because you are under the level of truncation, and then the Q character is complete. So let me show you first the graph mutation. So this is a graph in type A2, and if I mutated the vertex 2, 0 here, so I painted blue after mutating at it, so you know that there will be this diagonal arrow will disappear, and you will be left with this one. So if you continue, well, what we are going to do is mutate all the vertices in this column number 2 from top to bottom like this. So if you continue next one, you will get this. Now you have a new arrow, and this one has disappeared here. And you can continue like this, so which will now you see what it becomes. And then you can go like this as far as you want down. So I will say infinitely, okay? And then you do the same on the first column. So you first mutate at 1 minus 1, and then 1 minus 2, 1 minus 3, 1 minus 5. And you can observe that you restore the initial quiver. So after doing this 2 sequence of mutation, you go back to your initial quiver. And let me show you the same for type B2. So it's the same idea. You will first mutate in the column number 2. So I just display the result of all this sequence of mutation in the column number 2. You will get this after mutating in this column. Then you mutate in the right column. You will get this. So I have painted this one blue and the middle ones red. And here is a difference between the non-simply laced and simply laced, because here these arrows are smaller somehow. it means that you have to mutate 2 times now on the middle column. So we repeat mutation on the middle column, and we get now this blue painted vertices. And finally, we mutate in the left column, and we are back to the initial. So I want you to believe me that you can do that for any root system. And now I want to show what is the result on the level of cluster variables. Okay, so in order to have these Q characters written in the same way as in Kirillov and Reshetikhin, we have to make a change of variable. Instead of the variable z, which are here, we make a monomial change of variables. So in type A2, here is a graph again, and here are the variable of the initial seed. So you see, instead of having z2 0, z2 minus 2, z2 minus 4, I replace each z by the product of all the y's corresponding to the vertices in the same column, but upwards. Is that clear? Yes, and then I start mutating following the same sequence as we had before. So you see, you should interpret this monomial in the starting seed as being the highest weight monomial for some Kirillov-Reshetikhin module. So on the first row, y2 0 and y1 minus 1, these are 2 fundamental modules. On the second row, we have 2 Kirillov-Reshetikhin modules with k equal 2, k equal 3, etc. Now, when we start mutating at the first vertex, you will get this additional monomial, and you observe that the first monomial, which was y2 0, becomes y2 minus 2. So this is now the beginning of the Q character of the Kirillov-Reshetikhin module, but with spectral parameter shifted by minus 2. And this continues with other vertices like this. This is again the beginning of the Q character of the second Kirillov-Reshetikhin module. We have 3 additional terms, and the same here for the, and so on. And then I go to the second column. So now here you see it's even a little better, because I have not only 2 monomials like this, but 3 monomials. And actually I get the anti-dominant monomial, this y2 0 to the minus 1. So this tells me that in fact I have the full Q character of Kirillov-Reshetikhin module, because, okay, so I can go down like this. Here I don't write all the terms because there are too many, just the 2 extreme ones, etc., etc. And so I'm not yet finished, because the dual Coxeter number here is equal to 3. So I have 3 over 2 is 1.5, and I have done only once the sequence of mutation. So if I do it a second time, then I will complete the Q characters on the first column, and then I can say that I have all the Q characters of all Kirillov-Reshetikhin module up to spectral shift. And this works in full generality. Okay, I have now 2 minutes to explain the second part. I mean the geometric side. So it's going to be very, very quick, because so starting with the same graph, this graph G minus. So we can define a potential as, so what for this graph G minus. So what is the potential? It's a formal sum of cycles of the graph. And okay, in this graph here, it's easy to see what we are going to take: the sum of all triangles, which you see in this picture. And in general, it's going to be similar. Maybe, well, how do I go back? I don't know. Maybe, yes, I found it. So, for example, in this case, you will have cycles which are, I mean, it's not the initial seed. And so, yes, this one. So we take the graph of the initial seed, and here we have cycles which are triangles, but we also have cycles of length 4. And in general, depending on the entries in the Cartan matrix, we can have longer cycles.
What's the meaning of the Jacobian condition? Is it the composition of any 2 in a triangle is 0?
So for example, here, it would mean that if you take derivative with respect to this one, it would mean that the composition here is the same as the composition here. So here you have something of degree 2 equals something of degree 3. So it's a strange thing. It's no longer quadratic.
But for the
For the A case, yes.
This sum would
Yes, exactly. Yes, yes. Okay, so you get this potential, then you get a Jacobi algebra attached to this. And let me just say orally, so if we use this Derksen-Weimann-Zelevinsky theory, we can attach to this Jacobi algebra. I mean, we can look at certain representation of this Jacobi algebra, and there is one for each cluster variable, and we can describe, maybe I just write this formula, when you have M, a representation of this Jacobi algebra, then you can attach to it a certain F polynomial, which will be the sum of, let's say, over some dimension vectors E of all the, this chi now means Euler characteristic. It has nothing to do with before. Euler characteristic of Grassmannians of A modules of dimension E, so A submodule of M. And here you multiply by a certain monomial, well, which depends on the coordinate of the dimension vector. So you can form some geometrically defined polynomials like this. And the point is that they will give you, up to some dominant monomial here, they will give you the cluster expansion of all your cluster variables. And I want to show you the kind of representation that are associated. So this we call generic kernels. So in order to find this representation, you start from the indecomposable injective. So for example, in type A2, here is the indecomposable injective, which corresponds to the vertex 1 minus 2. It's infinite dimensional, goes down like this. And then you can look at another one, I 1 minus 4. And then you look at homomorphism from one to the other. And you have a notion of generic homomorphism and take kernel of this generic thing. In this case, it's very easy. The kernel will be just this two-dimensional module. And then you take the F polynomial of this two-dimensional module. And this is going to be a sum of 3 monomials, because these are just 3 submodules. And this is going to give you, after a certain change of notation, the Q character of the corresponding Kirillov-Reshetikhin module. So in this case, it's pretty easy. But let me show you maybe some. OK, let me show you type F4. So this is a graph. So this is a graph which defines the algebra. And here are, for example, pictures for the generic kernels corresponding to the fundamental module. So this is a fundamental module in type F4 corresponding to one of the end of the Dynkin diagram. And this is the one for the other one. So that's all. Thank you. Thank you very much.
How do you know, or how do you show these sequence mutations produce the higher?
Well, here we use the T systems. Yes, so here we are very lucky because we know that the Kirillov-Reshetikhin module, they satisfy some systems of polynomial identities, which are called T systems. This was proved by Nakajima in the simply laced case and by Hernandez in the remaining cases. And we show that, in fact, these T systems, along this special sequence of mutations, coincide with the exchange relations. And so we can keep track of this. And
The change of variable is to make from B to W.
yes. Yes, well, this is related with the formula. Okay, when you describe the cluster variable associated to this representation here, you have to multiply by a certain monomial with exponent the G vector, right? And so the change of variable is supposed to mean that you take into account or not this multiplication by this monomial here. So in the case of Q character, you could consider Q character or renormalize Q character, where you divide by the initial monomial and then it starts by 1. You see, these F polynomials always start by 1 because there is always a distinguished 0 sub-representation. So the first term here is 1. And so you have to shift everything by the highest weight. So the question, I have to repeat the question. Yes. So the question is whether this could be generalized to some general trees, but we did not think of this. So maybe, I have no idea. So yes, so I have to repeat the question again. So if we make arbitrary mutations, we conjecture that we would always get some Q characters of simple modules. Now, not only Kirillov-Reshetikhin modules, but many different modules. And this is a conjecture that we state at the end of the paper, but it's, for the moment, I don't see how to prove that.